Okay, the final question that was interesting is how many different ways can you color the vertices of a square using 5 colors so that adjacent vertices do not have the same color? And there's actually a little bit of subtlety to this. Notice it does not say all vertices do not have the same color. It says adjacent vertices do not have the same color. So if you looked up the definition, or if you asked, for instance, if I label my vertices 1, 2, 3, 4, adjacent vertices share an edge. That's the definition of adjacent. We saw that earlier, and we could have looked it up if we didn't remember it. So adjacent vertices share an edge. So in this example, it would be totally okay to give 1 and 3 the same color because they are not adjacent. So here is one perfectly okay coloring, and this one only needs 2 colors. Now, this one would not, this coloring would not be okay. I'm not allowed to have this because the vertices 1 and 3 are adjacent and they're not allowed to share a color. But colors are allowed to repeat. They just can't repeat on consecutive or adjacent vertices. So there are 2 cases to consider. Lots of times it helps to break our problem up into 2 cases. The first case is if we label the vertices 1, 2, 3, 4, the first case is that vertices 1 and 3 receive the same color. The second case is that vertices 1 and 3 receive different colors. Notice that color that covers all of the different cases. Sorry, receive different colors. So in this first case, there are 4 tasks to color the square's vertices. Task 1, there are is to color vertex 1. There are 5 ways. Task 2 is to color vertex 2. Repeat the same color, so 1 color is ruled out, so there are only 4 ways. Now remember, we're in the situation where vertices 1 and 3 receive the same color. So when I go to color vertex 3, that decision is already made. And I actually only have 1 way to color vertex 3. Task 4 is to color the last vertex, vertex 4. And there are 4 ways because the only color that I can't use is whatever I used for vertex 1 and 3. So again, I'm going to have 4 ways to color vertex 4. So for case 1, there are 5 times 4 times 1 times 4 ways. Case 2, vertices 1 and 3 receive different colors. So I have vertex 1, I have vertex 3 that have gotten different colors. Now I could have picked any of the 5 colors for vertex 1. So again, there are the square's vertices. Task 1 is color vertex 1 5 ways. Task 2 is color vertex 2 4 ways. Task 3 is color vertex 3. Now notice, I cannot reuse what I used for 2, but I also cannot reuse what I used for 1 because it says that 1 and 3 are different colors. So there are only 3 ways to color vertex 3. And finally, task 4 is to color the last vertex. Sorry, color vertex 4 here. Now I've locked out 2 of these. So I only have 3 ways to color vertex 4. So for case 2, there are 5 times 4 times 3 times 3 ways. And so the total number of ways is 5 times 4 times 1 times 4 plus 5 times 4 times 3 times 3, which will be, I think I'm getting 210. I have to add up case 1 plus case 2 by some principle. There are other ways to solve this problem that are valid. There's another way where you can break it up into cases. But unless you're in a situation where looking it up is not presented as a valid option, looking it up is always a valid option. So if you searched around a bit in the online encyclopedia of integer sequences, you would find a sequence that counts these things. So sequence A091940 says given n colors, this sequence gives the number of ways to color the vertices of a square such that no edge has the same color on both of its vertices. And that's exactly what we want. Now the question is, where does this start? So think of, because some sequences start at 0 and some sequences start at 1. If I have just one color, there will not be any way that I can do this. So just one color will force me to color adjacent vertices the same. So with one color, there are 0 ways. Whereas if I have 2 colors, and I count up, if I have 2 colors and I count up, then there are 2 different ways I can color this. So I needed to do a reality check. I'm not counting these 2 colorings as being the same. So I see that this sequence starts out 0, 2. So this 0 corresponds to 1 color. This 2 corresponds to 2 colors. This 18 corresponds to 3 colors. This 84 corresponds to 4 colors. This 260 corresponds to 5 colors. So I actually made a mistake earlier when I added this up. I should have not tried to do it in my head. This is going to be 80 plus 180. So the answer is actually 260, not 210. I had the right approach, but I made a calculation error. My fault. So this should be 260, not 210. There's a lot of really cool stuff if you look here. It gives formulas for these. So one formula that it gives is that if you have n colors, then the number of ways to solve this problem is n minus 1 plus n minus 1 to the 4th. So if I recognize that that formula existed by searching in the OEIS, a of n is equal to n minus 1 plus n minus 1 to the 4th. And so I could have solved a of 5, which is the number of ways to solve this, to color this with 5 colors, as 5 minus 1 plus 5 minus 1 to the 4th, which is 4 plus 256, which is 260.